Let us start, as usual, with a review of the previous class. I'm also going to take the opportunity to complete some details that I didn't have time to cover at the end of the last lecture. So we revisited the simple transitivity of the action of the Möbius group on the set of triples of distinct points of C bar. And what we saw is that that simple transitivity, which we had already proved, and actually very explicitly, and by very explicitly I mean by actually computing matrices whose Möbius transformation relate any given triple of distinct points to the points 0, 1, and infinity. So we revisited using linear algebra. And somehow what I argued was that the fact that I can send 3 distinct points to 3 distinct points amounts to noticing that the first 2 here form a basis of C2, or they are the P1 shadow of a basis in C2, and then I can send there is a linear transformation sending the first 2 to the first 2 vectors of the basis, and then to send the third one to the third one. Somehow, what I need here is to consider these 2 images of these 2 vectors, and then take one of the images and start rescaling. And then when I rescale, somehow the image of the third point starts moving around, and then there is exactly one way, there's exactly one value of the rescaling that allows me to hit the third point here. Right? So somehow this simple transitivity on triples of distinct points is the P1 shadow of the fundamental theorem of linear algebra, which states that given any basis of a vector space and any function from that basis to a vector space, this function can be extended in a unique way to a linear map. And also just notice that if I decide to rescale both images by the same scalar, somehow the linear transformation changes because I'm multiplying, I'm taking a scalar multiple of the linear transformation, but the Möbius transformation doesn't. Right? So that is why I really need only to consider rescaling one of the images of the basis vectors. Okay, after revisiting this simple transitivity, I introduced the cross ratio of quadruples of points in C bar, and I tried to motivate this the appearance of the cross ratio by means of the problem of finding invariant functions on Cartesian powers of C bar. And in the end, somehow the way I defined the cross ratio was not through explicit formula, but a rather more in a way conceptual, right? So because I said the cross ratio of a quadruple of points in C bar, not necessarily distinct. Right. Sorry. Yeah. I need the last 3 to be distinct, so that I can send them to 0, 1, and infinity. Right. So I send them to 0, 1, and infinity. Sorry. Right. And once I send them to infinity, I send them to 0, 1, and infinity. That is, once I have the unique Möbius transformation with that behavior, I apply the Möbius transformation to the first point. Right? And the result of evaluating that Möbius transformation in the first point, I call it the cross ratio. So I didn't define the cross ratio through an explicit formula, but I indicated how explicit formula can be found, right? I did it in the case where none of them is the point at infinity, and then we saw that it's that this could be expressed as the quotient of two products. Okay, and then I left as an exercise that it really is invariant on the action of the Möbius group. That is, that for any two quadruples, rho of the quadruple is equal to rho of the quadruple I obtained by applying a Möbius transformation, and that this happens for every Möbius transformation, right? So that it's invariant on every Möbius transformation. So this I left as an exercise, and then I saw that this is indeed somehow useful, right? So that introducing knowing that the cross ratio is invariant on the action of the whole Möbius group allows me to decide through computing this very simple number whether any 4 given points lie on a circle of C bar or not. Right? So if they give me 4 distinct points in C bar, and then they ask me, okay, so do they lie on a circle or not? Right? That is, if I draw the circle passing through, let's say, the first 3, does this circle pass through the 4th one? Right? And then the answer is actually quite simple. So you just compute the cross ratio, and the fact that they lie on a circle is equivalent to this number being a real number, right? So if the cross ratio is a real number, they lie on a circle. If the cross ratio has non-zero imaginary part, then they do not lie on a circle, right? So the cross ratio is a tool to decide whether any 4 distinct points lie on a circle or not. And then we went on to computing explicitly the fixed points of a Möbius transformation, right? So we already knew that a Möbius transformation different from the identity has at most 2 fixed points. This is because of simple transitivity. But the problems remained. If you give me the Möbius transformation by giving me a matrix representing it, how can I compute the fixed points of the Möbius transformation in terms of the entries of the matrix? Right? And that is what we did. Along the way, we showed that there always exists at least one fixed point. So there do not exist Möbius transformations without fixed points. Every Möbius transformation has at least one. Every Möbius transformation different from the identity has at most 2, right? And for the explicit computation of fixed points, first we first ask ourselves, okay, is infinity a fixed point or not? Right? And then first we gave a necessary and sufficient condition for infinity to be a fixed point, right, in terms of the entries of the matrix. And then, regardless of the answer, of whether it is a fixed point or not, we computed, and then we saw that finding the remaining fixed points, let's say, amounts to solving an equation of degree at most 2, right? Because somehow this equation is an equation of degree at most 1, and this equation is an equation of degree at most 2, right? Because somehow I pass this to the right, and then I obtain my polynomial of degree 2. So in the end, the fixed points of a Möbius transformation can be computed by first asking if infinity is a fixed point or not, and second, asking about about finite fixed points, right? So about whether there are fixed points different from infinity or not, right? And then in the very end, the problem amounts to solving a linear equation or finding the roots of a degree 2 polynomial, for which we know the quadratic formula. Right, and then we went on to state a theorem that relates the possible commutativity between two Möbius transformations, and somehow already a relation between some geometric data attached to the Möbius transformations, namely the fixed points. Right? So somehow the fixed points of a Möbius transformation are already somehow like geometric data. Right? They live in C bar. And the theorem was that two Möbius transformations different from the identity commute precisely if their sets of fixed points coincide. And here is where I only proved one direction, one implication, and I didn't have time to provide the proof of the converse. So, assuming that they commute, then knowing that one of them permutes the fixed points of the other, we went on to analyzing two cases: whether the fixed points, whether sigma has exactly one fixed point or two, right? And then if sigma has exactly one fixed point, then we argued, and then we came up to the conclusion that the set of fixed points are equal. And then in the case, in the case when sigma has exactly two fixed points, the first thing we noticed was that because of case 1, which was already proved, the other one has to have exactly two fixed points, because otherwise we could apply case 1 with the roles of sigma and tau reversed and deduce that then sigma would have exactly one fixed point, but against contrary to our assumption. Okay, so that was the first thing, that if one of them has exactly two fixed points and they commute, then the other one also has exactly two fixed points. And the rest of the argument was, well, now I know that both of them have two fixed points, so in order to show that the sets are equal, it's enough to show that one is contained in the other. Okay, so I took one element of the set. I want to see that it's in the other set. So what I do is I suppose it's not, and then try to arrive at a contradiction. Right? So I started arguing, and then I noticed the following. So I took a Möbius transformation with the property of taking the fixed points of tau to 0 and infinity. By a previous exercise, namely this one, taking the fixed points of something to 0 and infinity is the same as asserting that 0 and infinity are the fixed points of the conjugate. Right? So that's why if I take a Möbius transformation taking the fixed points of tau to 0 and infinity, I can immediately deduce that 0 and infinity are the fixed points of this conjugate. Okay, then I consider the conjugate of sigma by this same Möbius transformation, right? I presented it as coming from a matrix. And for this matrix, by doing some elementary considerations, I arrived at the following. This expression, kind of the Möbius expression, is equal to this applied to this, and then we saw that this one was multiplication by -1. Okay, but multiplication by -1. But you see here I made a mistake because I multiplied by -1 both of them, but it's actually I have multiplied only one of them. So let's say this one. So that was a mistake pointed out to me by one of you. Okay, so the final argument, what I said last lecture, which was that this would be 0, is incorrect, because what I can deduce is 0 is actually this one and this one, right? Just kind of from looking at that this is equal to this. So those are 0, and so what I deduce is that A is a diagonal matrix, right? So this means that mu A, which is this Möbius transformation, is equal to multiplication by alpha divided by delta, right? Because now I know that these are 0. Okay, but multiplication by alpha divided by delta has its fixed points are precisely 0 and infinity. Right? So what I deduce is that the fixed points of this conjugate are precisely 0 and infinity. That is, they are exactly the fixed points of this one. But you see, the point is I am conjugating with the same nu. So if the fixed points of nu tau nu inverse are precisely the fixed points of nu sigma nu inverse, then the fixed points of tau are precisely the fixed points of sigma. And then you may say, okay, that's exactly what you wanted. Well, actually, it's a contradiction, right? Because so actually what I'm getting is, assuming that Z1 is not a fixed point of tau, I can deduce that Z1 is a fixed point of tau. That's a contradiction. So what must be happening is that this is false. So Z1 must be a fixed point of tau. And then I move on to analyzing what happens with Z2. And then I apply a similar argument. And then I realize that Z2 must also be a fixed point. And now that is how I deduce this inclusion. And since both of them have exactly 2 elements, then I must have equality here. Let's move it so that you can see it. Equality here. Okay, and that finishes one direction, right? Namely, that if they commute, then they have exactly the same fixed points. Right? And now let us do the converse, which I didn't say a single word about last time because I didn't have enough time. So now suppose that their set of fixed points are equal. Right? Now we want to show that they commute. So I analyzed 2 cases, namely whenever there's exactly one fixed point or exactly 2 fixed points. Okay, but in both cases, somehow the underlying philosophy or the underlying strategy is the same. What I do is I take a Möbius transformation that moves the fixed point or the fixed points to a convenient location, right? Namely to infinity in the first case, or to 0 and infinity in the second case. And once they are in a convenient location, what I see is that in this case, right? They have to be both translations, right? So here, kind of the underlying statement that I'm making, that for the moment I leave as an exercise, is that if a Möbius transformation has exactly one fixed point, and that fixed point is precisely the point at infinity, C bar, then the Möbius transformation must be a translation, right? So, so from this equality, right, and then taking nu to send the fixed point to infinity, I have equality. So you see this is infinity, but then the fixed point of nu tau nu inverse is also infinity because of this equality, right? So both nu sigma nu inverse and nu tau nu inverse are translations. Okay, but you see, translations they always commute, right? I mean, a translation by a vector beta and translation by a vector beta prime, both compositions are translation by beta plus beta prime. So they commute, but if they commute after conjugating, then they commute before conjugating as well. Okay, and then in the second case, you see, once I sent the fixed points to a convenient location, I notice that something that for the moment I leave as an exercise, which is if a Möbius transformation fixes exactly two points, and these 2 points are precisely 0 and infinity, then the Möbius transformation is multiplication by some non-zero complex number. Knowing that, what I see is that both nu sigma nu inverse and nu tau nu inverse are multiplication by non-zero complex numbers. Maybe not the same, right? Maybe not the same, but in any case, you see multiplication by non-zero complex numbers commute with each other, right? I mean, this composition and this composition, they would both be equal to multiplication by alpha prime. Okay, and knowing that this commute, then after conjugation, then I know that tau and sigma commute before conjugation, right? So you see, for this one, the strategy is a strategy that is very commonly used in Möbius geometry, but also in hyperbolic geometry, which is take some Möbius transformation that sends the fixed points to convenient locations and conjugate your original transformation with that Möbius transformation. That's what I did in both of them. Right? And then I realized in each case, knowing that the fixed point or the fixed points are in the convenient location, I can say something about the conjugation, right? And then deduce what I want after conjugation, and then use the fact that conjugation preserves the property. So that was the overall strategy here. And one final remark. There is an exercise that is actually wrong, which is this exercise 10. Give an example of non-commuting matrices whose Möbius transformations commute. So it's impossible to give such examples, so this is wrong. Which means that in exercise 9, I actually have if and only if. So they commute if and only if their associated Möbius transformations commute. This direction is easy, and this direction is a bit harder. And somehow hint is the following. Consider the fixed points. So assuming that this commute, what you know is that there, if these Möbius transformations are not the identity, you know that their sets of fixed points coincide, right? And then you know that there is exactly one or exactly two. So try to move the fixed points to a convenient location and keep going to try and deduce this. Okay, and that is as far as it goes for the review of the previous lecture.